Wade.
Hey, Carly.
So today we're going to talk about one of my favorite theorems in statistics.
Your favorite one.
My favorite one, and it's called the central limit theorem, oftentimes abbreviated as CLT. So the central limit theorem is one of the most important theorems in statistics, and it actually involves my favorite curve, the normal curve. So the central limit theorem basically says that if we repeatedly take independent random samples of size n from any distribution or any population, the distribution of the sample means will approach the normal curve, especially when n is large. And as n increases, we're going to see that distribution of sample means looking more and more like the normal curve. And this is really powerful because if the distribution of sample means looks like the normal curve, then that means we can go ahead and use the standard normal approximation and Python, or if you want to use the table, to figure out different probabilities. So I want to kind of demonstrate the central limit theorem in action. And we're going to do this in two ways. The first way is going to be with a really simple random variable, which is just flipping a coin. So if we think about flipping a coin, and the probability of success is going to be the heads. So that is going to be 1/2. So our probability is 1/2. This would be a binomial random variable if we did it multiple times. If we did it once, we would call this a Bernoulli random variable. And I'm going to go ahead and just draw a probability histogram for 1 flip, 2 flips, and 3 flips. And we should see, if the central limit theorem is true, we should see that this probability histogram looks more and more like the normal curve the more flips we do. And then eventually, if we got to 100 flips, we should eventually see that the probability histogram is basically the normal curve. So for 1 flip, our probability histograms, we know, have the outcomes on the x-axis and their probability on the y-axis. So Wade, if we flip a coin once, what are my outcomes?
So if I think of heads as being a successful outcome, there's a 50% chance I got no heads and a 50% chance I got 1 head.
Exactly. So we can either get 0 heads or 1 head. And this is kind of a boring probability histogram. There's only 2 bars. The probability of success, like Wade said, is 1/2. So we would see something like this. So that doesn't look like the normal curve, right?
Not yet.
Yep, not yet. So let's go ahead and go to n equals 2. So if I flip a coin twice and I'm counting the number of heads, what are my outcomes?
So now we can have up to 2 heads. So 0, 1, or 2 heads.
Exactly. So I can have 0 heads, I can have 1 head, or I can have 2 heads. And if we wanted to figure out the probability, we could really quickly just list out the sample space. So I could get 0 heads would be getting a tail and a tail. 1 head, I could either get a head first and then a tail, or I could get a tail first and then a head. And then the only other outcome is getting 2 heads. So we can see if this is my sample space, the probability of getting 2 tails is just going to be 1/4 because there's one of those options out of 4 total. So I can go ahead and mark that on my histogram. The probability of getting 1 head, there's 2 of those out of 4. So that is 1/2 or 2/4. And then the probability of getting 2 heads, there's only 1 of those. So that is 1/4 as well. So Wade, what do I notice just when I go from flipping the coin once to flipping the coin twice about the histogram?
So this graph was really flat, and now we're starting to have a little bit of the normal curve kind of show up with the hump in the middle.
Yeah, we kind of see a graph that's symmetrical. It doesn't really look like the normal curve quite yet, but it's getting closer. And if we did n equals 3, we would get even closer. So here for flipping a coin 3 times, our outcomes are going to be 0, 1, 2, and 3 heads. And then we can calculate the probabilities kind of just like we did here. And so if we are flipping a coin 3 times, there's actually going to be 8 outcomes because for all of these, we can either get a head or a tail. So I'm just going to add, I'm going to write the same thing. And then I'm going to add a head to all of these. So if I got a head, I would add a head to all of these outcomes. And then I'm also going to do the same thing and add a tail. So we have tail, 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 head, tail, 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 head, tail, and then head, head, tail. So these are the 8 outcomes. The probability of getting 0 heads, it looks like there's just 1 out of 8 of those. What about getting 1 head?
So it looks like there's at least 2.
Right, there's this one, and this one. There's
3.
3. Yeah, so probability of getting 1 head is 3/8. And then what about getting 2 heads?
I see 1, 2, 3.
2, 3 as well. And then there's only one way to get 3 heads. And so here we see the central limit theorem in action. As we increase n, the number of tosses, our histogram is getting closer and closer to the normal curve. And like I said, if we got all the way up to 100 tosses, which would be annoying to draw, we'd see that the histogram would essentially be the normal curve. And the central limit theorem is known as one of the most important theorems in statistics and is going to come up a lot throughout this series.
I love that you can just see it with just a few coin flips, and I can imagine how this is becoming more and more normal, even though we know the coin flip itself is not a probability that looks normal at all.
Exactly, and that's one of the nice things about the central limit theorem is it doesn't matter what the shape of the underlying distribution is, this is always going to work.